anyway, it's part 2 of this video. Okay, so this question right here, this one with the megaliters, this is a tricky question. And what makes it tricky is it says there's 2 moles of nitric acid produced from 3 moles of nitrogen dioxide. So if we want concentration of nitric acid, what do we have to use? This isn't dilution, it's not parts per million, it's not percentage, we have to use unit analysis. Now we have some wonky units. It's up to you what you want to put them in. I'm just going to turn everything into grams and liters. A megaliter is 1,000,000 grams. So it's not 1.06 grams. It's 1.06 times, times 10 to the 6 grams. Okay, and that's nitrogen dioxide. So something's you're gonna see in a second what we're gonna have to do. Okay, we have 1 kiloliter. A kiloliter is 1,000 liters. We have a ratio of 2 mole nitric acid for every 3 mole of nitrogen dioxide. And what goes with mass? Molar mass. We need the molar mass of nitrogen dioxide. Okay, so we got nitrogen 1401 and 2 oxygens, which is 4601 grams per mole total. Okay, now, not to freak everybody out, this question is beyond the difficulty level of what's going to be on the test. But if you wanted to see how it's done, here we go. We need to get moles of nitric acid and liters of nitric acid, right? Molar solubility is concentration, moles per liter. So we're going to start with this little ratio because it's got the moles in it. We're going to go 2 mole nitric acid over 3 mole nitrogen dioxide. Now, where are we going to get the mole to cancel out mole of nitrogen dioxide? Right there. Mole 4601 grams. Okay, moles cancel. Oh, now we can put grams on top. Okay, that cancels. And we can put the liters on the bottom to get moles per liter. Now, again, this question is really tough because it throws something in that we'll be looking at in a future unit called mole ratio. But hopefully it kind of makes sense what we're doing. 2 times 106 to the 6th divided by 3 times 4601 times 1,000. Okay, and it works out to be in concentration to 3 sig figs, 154 moles per liter. Okay, that's kind of a tough problem. Don't worry, the rest of them aren't that difficult. Okay, next question. Alrighty. Okay, we'll get rid of this weird line. I don't know why that's there. Okay. So we've got 20 milligrams of solute is placed in 8,000 liters of water. What is this in parts per million? Oh, so what is it? Parts per million. Now there's 2 ways you can solve this. Let's just start with the formula. Solute over solution times 10 to the 6. Okay. Now the solute is in milligrams. We have to convert that to grams. We have to make the units exactly the same as on the top and the bottom. Or you can convert the liters to kilograms, then to grams, then to milligrams to make it the same. That's a bit of a pain in the butt. So I'm just going to scale the milligram up by dividing it by 1,000. So 20 divided by 1,000, and I get 0.02. Okay, putting that over the solution. Now that's got to be in grams. Remember, the unit on the top and the bottom have to be the same. So 8,000 liters is the same thing as a kilogram, but I have to times the kilogram by 1,000 to get grams. So 8,000 times 1,000 gives me a really big number. I get 800,000. No, 8 million. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Times 10 to the 6th. So now my unit on the top and the bottom are the same. Divide that by 8 million. 1, 2, 3, 4, 5, 6. Times 10 to the 6. And I get part per million is 0.025 part per million. Okay. Now the other way you can do this is, remember what I said? A milligram over a liter is already in parts per million. So you could just go 20 milligrams over 8,000 liters and divide it out that way. That's the shortcut. So 20 divided by 8,000, pretty sure it gives us the exact same value. Okay, next question. A bottle must contain 250 parts per million. If you drink a 1 liter bottle, what's the weight of minerals present? Okay, so we have our part per million formula, solute over solution times 10 to the 6th is equal to parts per million. Now, what do we know? Well, we don't know the solute. That's what's dissolved. We know we have a 1 liter bottle. 1 liter times 10 to the 6th is equal to 250. So divide both sides by a million. Okay. We got room. X over 1 liter is equal to 250 divided by a million. We get 2.5 times 10 to the negative 4. Now, if I times both sides by 1 liter, I know I'm running out of room. Times both sides, but that doesn't change it. So that gives me X is equal to 2.5 times 10 to the negative 4 kilograms. If you wanted that in grams, you would times that by 1,000 and get 0.25 grams. You times it by 1,000 again, you would get milligrams. Okay, next problem. Pool should be between 2 and 4 parts per million of chloride in the water. A 25 milliliter pool, blah, blah, blah. What's the total weight of chlorine? Okay, so again, we're solving for solute. So here we go. X over 375,000 times 10 to the 6 is equal to 3 parts per million. So guess what? Divide both sides by a million times both sides by the bottom. Cancel, times both sides by the bottom. And we get 3 times that huge number, 375,000. 1, 2, 3. And then we're going to divide that by a million. We get 1.125 kilograms or 2. That's a perfect number. There's really no good sig figs here, so we'll just leave it like that. All the sig figs are kind of messed up. Okay. All right, so we have an initial concentration of stock solution is 0.5. If 1 liter is diluted to 2, what's the new concentration? This is a dilution problem. C1V1 is equal to C2V2. Now, you could use common sense on this, but we're gonna just throw the numbers in there. So the initial concentration is 0.5 moles per liter. The volume of the first system is 1. The volume of the second system is 2. What's the concentration of the second system? Now, if you remember from the videos earlier in this week, so we're going to have to solve by dividing both sides by V2. If you double the volume, you half the concentration. Let's see if that checks out. 0.5 is our C1. 1 is our V1. Our V2 is, 2 liters. So 0.5 times 1 divided by 2 gives us 0.25. So by doubling the volume, we've halved the concentration. Awesome. Okay, we're getting close to the end here, I think. Or is there more? I don't know. How many questions did I give you guys? Oh, okay, we got 2 questions left. All right, so we've got blah, 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 blah. How much was the initial volume? So it looks like we have a final volume and we have a final concentration. It looks like we have initial concentration. So this is a dilution problem. C1V1 is equal to C2V2. Okay? C1V1, C2V2. Concentration of the first system. Remember, concentration of the first system is always the bigger number if compared. Because diluting it, you've added water, making the concentration smaller. Okay? What was the initial volume? We don't know. What was the volume of the second system? Well, it's 1 liter. Okay, so we're solving for V1. Divide both sides by C1 and throw our numbers in there. 0.089 times volume of the second system, 1 liter, divided by the concentration of the first system, 0.4. Decimal 0.89 times 1 doesn't change it. Divided by 0.4, I get 2, looks like 3 sig figs. The volume of the first system is 0.223 liters. Okay, so to make that 1 liter container, I would add water until it got to 1 liter. Okay, We got 22. This last one's kind of a tricky question, but I really like it because it's kind of like you have to do two questions within the same question. I always like those because they're challenging. For some of you, they make you cry. Maybe it's challenging and make you cry. I don't know. Okay, so here we go. We got 22 grams of sodium chloride, and that was dissolved in 500 milliliters of water. Later, it was diluted to 2.5 liters. What was the final concentration? Now, what you're thinking is, oh, this is a dilution problem. And it is, but the problem is, if we look at this question, we know the final concentration, okay? We know, no, we don't know the final concentration. I was standing in the shadow of the smartboard. So we know the final volume, we know the initial volume, but there's nothing else to go on. But interestingly enough, if we're given mass and volume, we can figure out the concentration that is, and guess what that's going to be? That's going to be the initial concentration. So this is a two-stepper. So listing what we know, we got 22 grams of salt, we got 0.5 liters of water, and what goes with mass? Molar mass. Okay, that gets me 5844 grams per mole. Okay, now I need to get concentration. So mole over 5844 grams. Okay, times 22 grams over 1. And I'm going to put the liters on the bottom. Okay, so now I get moles per liter. 22 divided by 5844 times 0.5. Okay, and that gives me the 3 sig figs 0.753 moles per liter. Now that is C1. That's our initial concentration. Our initial volume is 0.5 liters. We don't know the final concentration, but it's been diluted to 2.5 liters. So when we set up our formula, now we have enough to solve this. If we divide both sides by V2, we can plug our numbers in there. So concentration 0.753 times by the volume 1.5 over 2.5. So we throw their numbers in there. 0.753 times 0.5 divided by 2.5. I get a final concentration of 0.151 moles per liter. And that makes sense, right? We started with a more concentrated amount. Now that's our less concentrated amount, RC2. Okay,